In this video, we'll continue with crashing problems, but we'll formulate a question in a little bit different way. Your task is given here. So given the following network, calculate current time and cost and find the lowest cost to complete the project in 6 days. This table is given to you. Network is not given to you, but the activities and precedences are known. So you complete your network. So problems can be formulated like that. It can be combined. An AON formulation can be within some other problems. So that can happen in your quiz as well. It's really easy to develop this network. A doesn't have precedence, so that's the starting activity. B, C, and D all start after A. Okay, they're all here. And then E is after B, and that's the end node. Duration, how to read duration. There is normal time here. 3 for activity A, 2 for activity B, 2 for activity C, 4 for activity D, and 3 for activity E. What's our critical part? 3 plus 2 plus 3 is 8. 3 plus 2 is 5. 3 plus 4 is 7. So our critical part is A, B, E. We're only considering crashing activities on the critical part. Duration, that's the normal duration, is given in this column, and the crash time. Remember, by definition, crash time is the minimum time activity can be completed in. That's correct formulation of the problem. Just like given an example in the textbook. Remember, figure 9.3 that I was referring to in last video. And then we've got cost. Normal cost when the project is relaxed, network is relaxed, so there is no crashing. And then a crash cost when we increase the cost because we're reducing duration. And then we calculate slope. Slope is here negative. Why? It should be negative because by reducing time we increase cost, so it should be negative. But when working with dollars, obviously you're working with positive values. So what does normal and crash time here mean? Normal time is 3 weeks, but we can reduce it by 1 to complete it in 2 weeks. Please distinguish this by and in. Distinguish what's a crashing time and what's a maximum crashing time. So problems can be formulated differently, but this is correct formulation of a problem that you'll find in most books and not by shortcuts like in the problems behind chapter 9. That's why go by the example in your textbook. Okay, so here it's really simple. We're considering only 3 activities, A, B, and E. We have to crash it from 8, that's the project duration, down to 6, that's in your task. Okay, so what's the first option? Let's go by option A, reduce A, so that what's the crash cost? That's 40. And reduce B. What's the crash cost? It's 60. Okay, so altogether, total crashing cost is 100. Normal cost is 120. So the total cost will be 220, but we want only the crashing cost. So be mindful what's asking from you. Are we asking normal cost? Are we asking crashing cost? Or are we asking new total cost? So in this case, we're only looking for the total crashing cost. That's what's 100. Did we check the critical parts by reducing A? We're reducing this third part as well. So A is down to 2. Okay, this is crash days. So 2 plus 4 is 6. 2 plus 2 is 4. 2 plus 1 plus 3 is 6. That's all fine. We reduced it down to 6 days and we checked all critical parts. And the crashing cost is 100. There is another possibility. We can crash E. E here, actually, activity D here can be reduced from 4 down to 1. So normal duration is 4 days. Crash duration is 1 day, but it can be reduced one by one. So from 4 to 3, from 3 to 2, from 2 to 1 in steps, which means partial crashing is allowed. That's why here 90 is divided by 3, so that's $30 per day. But activity E is a little bit different. Activity E cannot be crashed partially. It can be crashed from 3 down to 1, nothing in between. So not from 3 to 2 and 2 to 1, but from 3 all at once in one go. For example, we need a special equipment to reduce duration of this activity. But that equipment has to be there only for that day, and it cannot be split. So we cannot do it partially. So we can do it only in one go. So some special conditions may exist in real life, and that's why I've shown you this example. And that's why this activity E with 2 asterisks have got a slope of -70, but for 2 days. It's not per day, it's for 2 days. That's fine, that fits us perfectly because we're reducing this part from 8 down to 6. Okay, so we can reduce activity E by 2 days all at once. So crash E twice because no partial crashing is allowed, and the cost is 70. Remember, this is 70 for both crash days. However, let's check our critical parts. So that's 3 plus 2 is 5 plus 1 is 6. That's fine. 3 and 2 is 5. That's fine. 3 and 4, 7. Oops. Okay, this is still longer than 6 that we require here in our task. So we have to reduce either one of them. To crash E, it's $40. To crash E, it's $30. Okay, so it's cheaper to crash activity D. Go for D. So that's $30. 70 plus 30, that's 100. We have shown both options. In this case, both options have got the same total crashing cost. It may be different, but it's important that we check all our options. It's a really simple problem. Only 2 options are viable to reduce this project down to 6 days, from 8 to 6 days. And one thing I'd like to mention here is reader's task. What does it say? Is it down to 6 days, down to 5 days, whatever it's asking from you? Don't do something that's not asked from you. Learn what's the crash time. What's the crashing time? It says in your book. That's the minimum time, the shortest possible time an activity can realistically be completed in. So a little bit different than the problems behind Chapter 9, but this is proper formulation. And the third thing I'd like to highlight is learn what we ask. What are you looking for? Are you looking for the total crashing cost, or are you looking for the total cost? Because total crashing cost and normal cost give total cost. But here we didn't look for the total cost. We just look for the cheapest possible way or the lowest cost to complete project in 6 days. That means we're just comparing total crashing cost. Okay, so this is just a simple, very simple exercise, formulated differently, but no differently than your example within the chapter. This is the proper formulation of the problem, but very simple as well. So have a look, make sure you understand definitions, you understand what you're calculating, and you understand what's required from you, and read the task several times so you don't make any mistakes there. And with this, we have covered Chapter 9, all computational and quantitative problems. And the next video will be talking about value analysis.